So we'll introduce a certain factorizable ind scheme. It's called local regular opers, regular local opers. Again, factorization scheme. Sorry, unramified. And we'll consider ind co of that. It will be factorization category. So and let me emphasize that so for the group G check, and so this will be a very precise Galois analog of the local, well, the factorization category, the Whittaker category on the spectral side. So that's what it will be. So then, analogously to this, so as Dario explained, there's a functor of coefficient that goes from D modulus on Bangui to the round version of the Whittaker category, and well, it has a functor, it left a joint called the Poincare series. And similarly, we have, so you have quasi-co, Oloxis G check, and there will be a functor. So I'll take this int co of unramified opers, take the round version, and there will be a functor of spectral Poincare series. All right, so that's, again, it's just analog of what Dario had. And so now we will connect it to the automorphic side. So let me remind that, so what Dario did, he on the, so for Whittaker, so there was this factorization category Whittaker, and so his talk yesterday compared it to the spectral side, so that was the factorization category corresponding to rep G check. And so, and I want to emphasize that it was kind of the first time Langlands duality appeared, in the sense that that's the first time we actually passing from between the automorphic side and the Galois side. We're not doing it on D mod Bangui and quasi-co Oloxis check as we want to, but we are passing on some local categories and some round versions of factorization categories. So here we'll have a similar thing. So we'll have a certain functor that will go from int co of this opers unramified G check. So, well, in fact, functor will go the opposite direction from this Kazhdan-Luste category that we talked about at, so let me pull critical level. So it'll be critical, so we talked about level for Kac-Moody. Here the level will be minus half of the killing form. So critical means that. So its functors, I call it ds, and it's called ds for Drintville-Sokolov. And I will explain what this functor is. Conjecturally, this functor is an equivalence. So we know it. So we want this to be an equivalence of factorization categories. What we know is that it's equivalence over 1 power of the curve. And Georgia is working to prove it in general. Okay. Okay, and I want to emphasize that this is, again, so this is the spectral analog of this equivalence. So like, again, this is something familiar from number theory. Kind of Whittaker is supposed to read off directly the Galois information. And here it'll be kind of the same thing on the spectral side. All right, and finally, so I want to create what I call the fundamental diagram that Dima will exploit in his next talk. And so the fundamental diagram reads as follows. Sorry.
No, it's fine.
I say spectral because I'm used to Galois. Yes. All right. So, and it will look as follows. Here I have Kazhdan-Lustig for G at the critical level over the run space. So and I have this localization functor that Nick was talking about to D modules on bun G. Again, so we didn't really talk about twistings for the lack of time. So let me say that this twisting is integral, so you can identify the category of twisted D modules with the category of untwisted D modules. So let me just sweep it under the rug. Don't worry about this for a moment. So here we have this functor of coefficient, and I'm not doing the extended Whittaker, I'm doing the usual Whittaker. So, and that goes to the Whittaker category on the run space. So, and again, just look, I'm doing the, well, it's like this localization against Whittaker. Now here I have intco of these on these opers. And it's my phone, very embarrassing. Let me just see. Белка, я сейчас не могу говорить, я на лекцию, я просто ее читаю. Да, пока. Sorry. All right, so here we have this quasi-co. And again, it's really quasi-co. We don't feel this correction with intco here. So there's this Poincare series for G-check spectral. And here we have this functor of co-localization for G-check. So it goes to rep G-check run. And this is the functor that, again, Nick proved for us that it's fully faithful. Again, we want to have an equivalence here, but we don't yet have it quite yet. Here, it will be functor of Drinfeld-Sokolov, and here is this functor Dario. How did you note it? Whittaker. Pardon?
I copied your notation.
Okay. So, and what we'll prove is that we want an arrow here. We don't quite have it yet, but what?
Two sides don't match because we don't have info in the meters. So.
Yeah, they're not supposed to match.
Yeah, so just stop saying that we want an equivalence.
Yeah, yeah. A functor. We do. Oh, yeah. So if Leah sees that, it'll be the end of me. No, coffee spilled. So, all right. So, so I call this fundamental diagram. There's no error here, but we'll prove this diagram is commutative, and that will be our tool for the proof. And again, so just I want to emphasize, it's like Kazhdan-Lustig versus Whittaker for G, and here it's Whittaker versus Kazhdan-Lustig for G-check. Just perceive this as a Kazhdan-Lustig version on the spectral side, and this is a Whittaker version of the spectral side. So this is what I call the fundamental diagram, and I'll say some words. What? Yeah, well, kind of whatever symmetry it exhibits, and I'll try to explain the best I can why it commutes. Well, there's a fuller proof in the notes.
But so in what sense is the bottom the spectral side? I mean, it seems like both of them involve the...
Pardon me?
In what sense that this bottom arrow is the spectral side?
So I'm saying that this functor is a very precise analog of this functor. If you go to this quantum deformation, they kind of, this functor and this functor will become completely on an equal footing. So basically, kind of this local equivalence, let me just put it quantumly. So it will be Kazhdan-Lustig G at level kappa for the group G, and it will be Whittaker for G-check at level -1 over kappa. So this is what will happen for general level. Here our kappa is critical, and in this case, kind of 1 over kappa becomes infinity. And so this category degenerates to this. And here it will be the same thing, but with inverted roles. It will be Whittaker for G and Kazhdan-Lustig for G-check. Does that answer your question?
I don't think so. I thought that the spectral side is the things on the right
So
hand side.
our spectral side is the right-hand side. Yes. But so what was the question again?
But this one is horizontal, so it also has a left-hand side.
So it's the comparison between Kac-Moody on the automorphic side with Whittaker on the spectral side. That's what I'm saying. And here it's comparison of Whittaker on the spectral side with Kac-Moody on the Galois side. But what I wanted to emphasize that the words Galois and automorphic should be erased, in a sense, because once you introduce the level, they really become symmetric. There's nothing. So Galois is just spectral at level infinity.
Just when you have level infinity, can you somehow check that this diagram is commutative? Because you do have the functors.
So this is the fundamental diagram, and I will prove that the diagram is commutative.
The full diagram.
Yeah. So the outer diagram.
No, I'm including the bottom line.
I mean, there's no bottom line. This is just this is the specialization of this. I'm saying that when kappa becomes critical, this arrow becomes this arrow.
I see. So what did I want to ask? But there is, in principle, another diagram you can write also at level infinity and critical. Right? You can sort of interchange the roles of
It'll be adjoint to this diagram.
adjoint in that sense.
You take adjoint functors. So you can, instead of coefficient, you put Poincare series instead of localization to localization. There is another diagram, but it'll be kind of, its commutativity will be formal consequence of the commutativity of this one.
So okay, so you will prove that this diagram is commutative. So there are 6 sort of vertices of this diagram.
Yeah, but only 4 arrows, because I don't have the arrow in between. So it'll be
So let's say 6 arrows.
why 6? Well, this is 1 arrow combined.
Oh, I see. So you mean that commutativity somehow, to prove commutativity, you don't need the middle line.
Well, there is no middle line for now. We'll create the middle line by proving the commutativity. Do you see what I mean?
So that means that you're going to explicitly describe the functor from Kac-Moody to
Exactly. Well, it's described explicitly in the notes. I mean, I'll do whatever I can. All right, so now I have to tell you who these guys' opers are. I might not be the best person to do this. So, pardon?
Who will be the best?
I think Frankel is the best person to do opers. So let me just poll people who have seen the definition of opers. Who has not seen the definition of oper? Great. All right. Okay, opers it is. Okay, just so that I don't put the checks all the time, when I talk about opers, I'll be denoting my group by G. So we'll be doing it for G check, but let me just denote it for G. Okay, so first some basic Lie algebra. So if you take your G, yeah, and also for simplicity, I'll assume that G is adjoint. Just in the notes, I'll explain what to do in the non-adjoint case. So there is a Borel inside, and then you create there's a filtration on your Lie algebra, so that kind of these, well, increasing filtration, that the 0th term of the filtration is the Borel. Say G minus 1 is n, and, well, G1 is Borel plus kind of negative simple roots. So then, if you consider G1 modulo B, this is canonically isomorphic to n minus divided by its unipotent radical, and note that it's canonically isomorphic to, well, the product of R copies of A1. Okay. Well, the negative simple roots, kind of, it has a basis. And so we denote by non-degenerate, it's the open part here where, well, you forbid zeros along each of the coordinates. So it's AR, take out the kind of the coordinate hyperplanes. Okay? So, and you denote by G1 non-degenerate. It's, well, it's open subvariety in G1, which is the preimage of G1 mod B non-degenerate. Okay, so I will now give the classical definition of opers. So kind of in this workshop, as we mentioned the first day, we have to do things in derived algebraic geometry, but first I'll do it kind of in classical algebraic geometry. So I'll define the D scheme of opers. So it'll be certain opers G check, opers G. Note, it's called regular, and I'll call it X deram. Well, maybe I'll put regular lock, but so it'll be actually, and maybe it's silly. Okay, just it's silly. I mean, it's just to keep in line in my notation. Well, I wanted to keep consistent notation. Just forget it. It's just, and it will be an affine D scheme. So it will be an affine map.
I want to first give a definition for GLM.
Great idea. Okay, let me tell you what kind of object it is. So what does it mean to produce well, not even an affine D scheme. What does it take to produce a D scheme? So it takes the following. By definition. So if you have any scheme, well, Y, well, over X deram, and what I mean, again, we're doing classical geometry, all I mean, it's a scheme over X equipped with a connection along X. Again, ordinary algebraic geometry, just let me choose. So scheme equipped with a connection along X. This means that you can locally differentiate functions on X, on Y, with respect to vector fields on X. You know, if you've taken a course on differential geometry, well, you know what the connection is. All right, so I have to tell you what it means to map Y to opers. Well, as D schemes. So again, this is also a D scheme over X, and I want to say how to map one into another, preserving the connection. I'll describe the functor of points. And so, okay, it's what's called opers on Y. So let me tell you what they are. And as Sasha is suggesting, I'll first do the case of GLN. So it'll be.
GLN is not a drawing.
Damn it!
Sorry.
It is.
No. Well, but
For other purposes, I mean.
yeah, we'll do GLN nonetheless.
Dual group, it's the derived group, but dual group is simply connected.
That's fine. No. Okay. So it's called opers on Y. Okay, opers with respect to G. I don't know where to put the script on Y, and let me tell you what they are. But we'll do GLN first. Okay, so all this stuff was needed to set up an arbitrary group, but GLN is much easier to say. Okay, so the datum of a GLN oper on Y is the following thing. So you have your Y, and then you do, so it'll be rank N is GLN, vector bundle, on Y, equipped with the following two pieces of data. With. So on the one hand,
There's no, why there's no F? Is it Y cross X?
no, Y is over X. Y is D scheme over X.
Y is over X.
Yeah. So the first piece of data is a connection. So along X, i.e., it's a so note that if you have just y over x, in order to and you have a bundle over y, in order to speak about the notion of connection on this bundle along x, it only makes sense if you already So if you want to speak about connection along x, it only makes sense if y had a connection along x. So like if you try to formulate what the Leibniz rule means, you will need to know how to differentiate functions on y with respect to vector fields on x. So that's one piece of data. Second piece of data is a flag, reduction to the Borel. So 0 equals E0 in E1, complete flag by vector subbundles, En minus 1 En. And there is a condition. The condition is that these two pieces of data are incompatible. This flag is not preserved by the connection. If you differentiate, you don't stay within the flag, but the condition reads as follows. So nabla of EI, but it moves it by not more than 1. First of all, so nabla of each EI is in EI plus 1. And then, so kind of if you wish, that's condition. It's a closed condition. So I'm saying that you don't go too far. Pardon me? Oh, tensor omega. Thank you. Okay, now given this condition, so if you know this, you'll see that nabla defines a map from EI modulo EI minus 1 to EI plus 1 modulo EI, tensor omega. But if you look at what the Leibniz rule says, you will see that, well, how does Leibniz rule work? Do you guys know? I don't, it doesn't matter. But what you'll see is that this map is actually OX linear. So like this differential operator of order 1 disappears. So this is an OX linear map, and know that these are line bundles. This is a line bundle. It was a complete flag. This is a line bundle. And so we have an open condition that says that this map is actually an isomorphism. So which means that the connection moves the flag by 1 step and exactly by 1 step. So that's what's called an oper. Looks weird, huh? Complete flag, yeah, see. Pardon me? So these are opers for GLN.
E is on Y, right?
E is on Y. Bundle on Y. All right, so okay, so let me poll the audience. Do you guys want to see the definition of arbitrary G? Or do you? Okay, let's.
Principle.
What?
We got the principle.
You got the principle. So
Just say that somehow it's the data is the same and the condition, and given x is to formulate the condition, given what was in the middle of y.
okay, is there anybody in the audience who would object to this? Is there anybody who craves to see the definition of oper for an arbitrary group? Great, excellent. So, okay, I'm totally in line with that. So the hint is that use this G1. Use this G1 and use G1 for the condition A and B for G1 non-degenerate for condition B. Yes.
Can you tell us what's this definition? I mean, what is this?
Yeah, who are these guys? So there were these dudes, Drinfeld and Sokolov, in 1987, who wrote this definition in this long paper. I don't think they had Langlands in mind then. Who knows? Drinfeld might have. Well, I don't know what he had in mind, but well, I really don't believe that he had. And I don't. I'm sure. Well, he knew that. Well, it's kind of obvious. He knew that it's analog of Whittaker, which will I think it will become clearer in a couple of minutes. But okay.
But they created the DS arrow then?
Pardon me?
They created the DS functor to
No. DS functor involves Langlands duality. They didn't have it yet. They gave the definition. So basically, kind of what the paper is about. So they explained that this kind of space of Opers is the natural place where the KdV equation lives. So that's what they explained. So KdV flow naturally takes place on the space of Opers on the formal disk. So that's the essence of the paper. So if you write this funny KdV equation, so the most natural way to interpret it is, and we have an expert on this here. Where are you, Pavel? All right. All right. So what I have to do now,
About why, so you define it as a D scheme by definition, right? Because you somehow
that's
as
it.
a functor on D schemes over 1.
Yeah. Okay, so what I want to do now, I want to, it's all well and good, but that's not what we need. So these are what's called regular Opers, and we need what I call unramified Opers, and these are different things. So now I have to get more technical and kind of redo the theory in the way we did everything.
Can you just say really fast why they're called Opers?
Pardon me?
Why are they called Opers? Yeah, and what?
So I don't know who coined the term Oper. So maybe,
It really has to do with operators, I think, and it has to do with operators because for GLN or for SLN, when you do it like on the disk, you can think of them as differential operators.
yeah.
I think that's kind of.
Pardon?
Doesn't it mean cop in Russian?
No, it's a joke. No. It meant operators. I don't know. So I think at the time when the Drimfeld-Sokolov paper was written, so they didn't call them Opers. I don't know. I don't think they called them anything. So. Okay. So let me proceed with my program. So what we need, we'll need these guys over the formal disk, and okay, so now we'll have to do a bit of something technical. Where am I? Okay, so now we'll face the question of what are connections on the formal puncture disk. So, pardon? For our purposes? Yeah, we'll get there. But I still have to define. Right. But that's a D scheme, but that's not quite what we want. So I'll spend some time describing the object that we really need.
Maybe it's worthwhile to say that if it's a D scheme, what happens if it's horizontal sections?
I'll say all of that. Okay, so let's recall that we had this factorization space jets horizontal into BG. And we also called it log sys with respect to G on the formal disk. And that was our definition. So, and it kind of, its fibers. Right, yes. I am defining what are local systems on the formal puncture disk. And I need that. No, local systems.
But eventually, what is the next?
Eventually, I want to define this factorization space, which is unramified Opers. Well, this.
It's helpful if you first define it global sections.
You can't.
What do you mean?
It,
Just you can say what the opers in the global curve. I think it will be or just single workers.
let's not do it, because
Didactically.
no, didactically it won't help. So let me do the way I wanted to do. Maybe we'll sink the ship. It's okay. Okay, so to proceed logically, I have to define what I have to go back and recall what local systems are on the formal disk. So recall that local system on the formal non-puncture disk were defined as this. So it's a factorizable space whose fibers at, let's say, at point x1, xn, distinct points, is just a product copies of BG. That's what it was. Okay, but now I'll give you a different interpretation. So we'll consider the following factorization space, namely consider jets, well, not horizontal, into G tensor omega x. Well, you can imagine what it is. It's a vector bundle over your curve, and you take jets. So again, the factorization space, if you take x1, xn points, x1, xn, you will, well, you'll just get a product of your one forms on the curve, well, tensored with the local ring at these points. So one forms on the parametrized formal disk. Yeah, make sense? All right. Now, so one thing I will assume that you guys know is what it means, what gauge action means. So if you have a variety in a one form and you have a map from your variety to a group, so you think of one form as a connection of the trivial bundle, and if you act on your trivial bundle by an automorphism, this connection form will go to something else. It's called the gauge action. And so we consider the quotient of this by jets into G. So this is one form's modulo gauge. And so both are factorization, well, in fact, factorization affine schemes, and you form this factorization pre-stack, just quotient, and you sheafify it in the Étale topology. Well, you've got that. And then there comes the theorem that, well, let me just call it forms modulo gauge. That, so there exists a natural map from log sys G hat into this forms over gauge. And it's an isomorphism. So in fact, your factorization space of local system that we've been using for, well, for this log on logs log functor can be expressed in these terms. Step number 1. People confused already? Again, forms modulo gauge. There is something to prove here, but it's not very difficult. Okay, and now, so we are ready to say what local systems are on the formal puncture disk, and there is no surprise, but it's a poor man's definition. So you define, so now you consider the following. You consider now meromorphic jets into G omega x modulo meromorphic jets into G. Call this quotient, let me call it forms modulo gauge meromorphic, and define log sys on the puncture disk. It will be a factorization pre-stack to be that. So take this quotient, you sheafify in the Étale topology, and that's your thing. So this must sound very anticlimactic. So like you kind of...
What did you say again?
What?
Just can you repeat the sentence?
I'm saying that this definition must sound very anticlimactic. Because, well, it's kind of really poor man's definition. So like we're doing all this fancy stuff, but now you can't really do all this Deram, blah, blah, blah. And at the end of the day, to give the definition of connections on the formal puncture disk, well, you go back to kind of level 1 and you say it's forms modulo gauge. And the reason we do it is that we don't have any other definition. Pardon? Yeah, so for this discussion, G is G-check. Oh, sorry. Just, I mean, it's only one group for now. Pardon me? Neuromorphic. Who asked? Oh, yeah.
What happens if you'll try the usual definition of boxes? Why would it work?
So the problem is that so this symbol I was trying to explain on day 3. If you do the disk, but not formal, but just disk, if you put deram, you get nonsense.
Oh, because you don't have the generic point.
Well, no. So this has a generic point, but if you take if you do the in scheme disk, you take deram, you get the point, and that's what you want. But if you do the spec version, if you do deram, you get nonsense. That's not what you want. So therefore, if you even punctured, you'll get even greater nonsense. So you don't want that.
So what if you do it by hand, like approximating D with finite type schemes?
No, but it's, you see, so it's not the finite typeness that's the problem. Like forget time, just take D and take deram. You want to see the point. Like local system with a non-puncture disk is supposed to be just G-torsors. And that's what you're not seeing. Like it's just large.
And if you take the formal disk and portion it by the formal disk, that'll give you the same thing as the RAM. So it'll give you nonsense.
Say again?
You have an action of the formal disk on the disk.
What do you mean action? Whoa.
Well,
What?
They're both groups.
Oh, jets on the. No. I don't think you're saying. No, I don't think what you're saying. I don't think what you're saying makes semantic sense. But
Just to define it, define it by just separately define a connection with given order of pole, and then take the limit.
so
I mean, given order of pole, it's like
okay.
single object to connection.
for GLN.
Yeah, just GLN. You can restrict. GLN won't help. So the problem is the following. So see, when you take given order of pole, fine. Order no greater than 5. Yes. What acts on these guys? There is no group, there is no subgroup in the gauge transformations which preserves connections with pole of order 5. So the only group is G of O.
Yes.
But you want to impose more equivalence relations. There are connections with pole of order 5 that are gauge equivalent under G of K, but not under G of O. But once you start doing G of K, you start with pole of order 5 and you'll get a pole of order 27. So I mean, so there is like once you are away from like regular connections, there is no particular level at which you can stop. You must take them all at once. So just one second. Well, exactly. Pre-stack. I can't say anything better. Yasha, what are you saying?
What is bad about this definition? As you told us, also
If you're happy, I'm happy.
no, you don't have to shiftify. No, the reason why, for example, affine Grassmannian, you want, for example, don't consider the Gaussian because you want to consider as a geometric object. If you interpret only sheaf on it, you don't have to shiftify.
Okay, so Yasha seems to be happy. Let's proceed. Okay, but that's the definition. So we could see we could discuss the relative advantages of two definitions if we had the second one, but we don't. So yes.
There's a possibility of using non-Archimedean geometry.
Well, yes. Kobe also suggested that. I'm ignorant about analytic geometry. Maybe. So my understanding is so poor that I don't even know what questions to ask. Yes, it's a good question. If you can work it out, it'll be great. If you can create something sensible and, yeah.
All problems come from the fact that the puncture disk is not a space, but a diagram of spaces.
If you wish. So yeah, maybe let me just make it even more kind of sharp. So again, the non-puncture disk, what we really want to think about is the in scheme. And then, but the non-puncture, the puncture disk, we have to go to this ugly scheme, and then that's the problem.
It's a scheme over an in scheme.
Yeah, yeah, and it's kind of Travis. Great question. Not meromorphic, but jets horizontal meromorphic. You can, and you arrive to the same, and it's in the notes. It's possible.
So this is an alternative.
Well, but it's alternative, but it's the same. So one thing you have to do, we have not defined jets horizontal meromorphic. We haven't done it, but it's done in the notes. It's not a straightforward definition. Like again, you cannot use D not the RAM. You have to do something else. So again, it's written.
What did Travis ask?
Pardon?
What did he ask?
He asked, why can't we do jets horizontal meromorphic into BG? You can, and you'll arrive at the same definition. But you have to know what this is, and we haven't done it. So on day 3, I didn't do it. I only did non-meromorphic. Meromorphic kind of involves D naught, and the RAM of that, you can't do that, you have to do something else. All right. So, so with these definitions, we still have the map from log_sys G, log_sys from the non-punctured to the punctured, and lemma is that, well, like usual jets embed into meromorphic jets. So we have this map. The map is that it's I should say int closed embedding.
Is the special property of BG, or will it be true always when it comes to meromorphic?
I don't know. So, well, it's a good question. For some reason, I didn't ask myself this question. So, closed embedding means that, so both are pre-stacks, means that if you base change by an affine scheme, you'll get what you will get. You will get an ind scheme such that each of its closed subschemes closedly embeds. So why it's not a closed embedding? For example, you have infinitely many points embedding into A1. Like take Z embedding into A1. This is not a closed embedding. Like Z is not the very closed subset in A1, but Z is a union of finite sets, each of which sits closedly in A1. So that's what I call int closed embedding. It's this kind of phenomenon.
So, can you give a definition or whatever?
What? What it means in int closed embedding? I just gave it.
You didn't.
I just said it.
You gave an example.
No, I said that if you base change by an affine scheme, the base change will be an ind scheme such that the map of each of its closed subschemes in is a closed embedding.
Oh, so your Z is you regard it not as a scheme, but
In scheme, yeah. All right. Well, actually, it's wait. Great. Okay. So now we can go back to our opers. No, I would like them to be the same. Okay, so now I'll redo, so now I'll define 3 factorization spaces. It'll be opers, regular, it'll be opers meromorphic, and in between there sits something that what I'm really after, it's opers unramified. This is UNR, unramified. So I'll define the spaces, and in a second I'll comment what it has to do with just this scheme of opers. So, so I'll first define this guy. Well, it's defined. Okay, so I didn't define opers for you in general, but now I'll do it. I'll take this G. Instead of taking jets into all of G tensor omega, I'll take jets into, well, this guy. And, sorry, 1. First term of the filtration. Borel.
Which was N plus, or B plus.
Well, B plus plus a little bit plus the negative simple roots. G1. So you take jets into this, but also to the non-degenerate part. The Borel. So this is that's what it is.
So compared to the definition you gave before,
I'll compare it in a moment.
there's some theorem here.
Yeah. Pardon? This is gauge action. Just as before with connections, but it'll be gauge action, but on this set. So and yes, at tau localize. So now you can take jets meromorphic. Again, non-degenerate, and divide by jets meromorphic into B, and this is what I call meromorphic local opers. And finally, so let's note the following, that by the very definition, kind of the way I set up my local systems, I have forgetful maps. I have opers meromorphic guys map to log sys G on the puncture disk. Well, just this sits all of G inside all of G, and the Borel sits inside G. So they have this forgetful map. So, and inside here, we have log sys G on the non-puncture disk. And you also have this log kind of regular opers. And you have, so you have a map like this, and you have a map like this. Kind of. Now, why did I write this diagram? Why is this arrow slanted? Pardon? Yeah. So okay, there's of course this map, but this diagram is not Cartesian. So if you take the preimage of regular local systems inside meromorphic opers, you'll get more than regular opers. And so unramified opers is something that sits in between by definition. So that's fiber product. So it's you really get so like you can. Yes, I kind of see there are many things to say. I don't even want to go there. So all I want to say is that you can have one form which has poles, and it's not B equivalent to one without poles, but it may be G equivalent. You can apply gauge transformation with G to make it to gauge away the poles. And so this is why kind of unramified opers is strictly bigger than regular opers.
But still, this fact that you're using here, that there are two forms which don't have a pole,
Absolutely. So, yeah. So, yeah. All right. So now, what does this have to do with the previous definition that I gave? So again, there are more details on this on the appendix, but so if you have y deram, let me call x deram over x affine y sub x deram, so relative affine scheme, x deram affine scheme. Well, we can consider, well, we defined jets horizontal of y x deram, and this is a factorization. It's a factorization in the scheme, and we did not define jets horizontal meromorphic, but again, I refer to the notes how you do it. So in the affine case, it's particularly easy. So this is a factorization scheme, and this is a factorization in scheme. So if you look carefully at the definition, and if you plug in y x deram to be opers as I originally defined at the beginning of the talk, you'll recover this and, well, meromorphic opers respectively. So in fact, I did not have to spell out this definition. You basically start with opers as I defined it at first and take horizontal jets and horizontal meromorphic jets. So I'm saying that kind of lemma, take y deram to be opers, where this was what was defined at the beginning of this talk. Yeah, so it's that D scheme that we started from. Then I'm saying that if you take jets horizontal into it, pardon? There's no y. There's no notation y.
No, your previous notation was y sub x deram.
Oh, sorry. Sub x deram. Then this is opers regular local of G. And similarly for meromorphic.
What do you mean? I mean, there should be some curve. The curve x should appear here.
So this is a factorization space. So these are the quality of factorization spaces. So you recover this as by taking jets into the original thing. And you recover meromorphic opers by taking meromorphic jets into the original thing. Meromorphic, horizontal meromorphic jets.
Right, and global opers in x.
Coming. Coming. So maybe we should take a 10 minutes break and then I'll do global opers.